Okay, so I think we can get started. All right. So last class we talked about some general concepts of the coal-fired power plants. I think now, I hope you guys have a more clear understanding of what type of system we're dealing with. I hope that you're not more confused by now. So still, if you're confused with anything, just let me know. Okay. And also, I think it's nice to discuss with your group members first, right? And then to try to tackle the problem within the group first, okay? So this class, we're going to start to learn a new air pollutant. So we mentioned that there are 6 criteria air pollutants, right? We have to deal with the particulate matter and the sulfur dioxide. And now this class, we're going to talk about the nitrogen oxides, okay? So just as a recap, we learned about the sulfur dioxide control. So we mentioned that for sulfur dioxide control, there are 2 ways to control them. So one is the fuel desulfurization. That is just to remove the sulfur. That is just to remove the sulfur inside the fuel. So we mentioned that there is a process called the Claus process, which can convert the sulfur in the fuel first into the hydrogen sulfide. And then we can let the hydrogen sulfide to react with the sulfur dioxide and form the solid sulfur, right? And that can be sold for money, okay? And we mentioned that this is mainly used in the oil refineries, mainly because the oil is in liquid form. The reaction is more complete in this way, right? But if we're talking about coal, which are solid fuels, the reaction is going to be incomplete. It's very difficult to go through these reaction processes. So that's why we learned about the flue gas desulfurization. Okay, so the flue gas desulfurization mainly deal with the sulfur that are basically generated into the sulfur dioxide. Okay, and we use the limestone scrubbing as the example to learn about the sulfur dioxide control, which is basically pumping in the flue gas, right? And at the same time, we're going to spray water droplets that contain limestone. And we call this entire system as the scrubber, okay? So we mentioned that there are 2 important parameters involved in the design of the limestone scrubbing. That is, first, the limestone feed rate. So based on the stoichiometry, based on the purity of the limestone, and also based on the composition of the flue gas, we should be able to calculate the feed rate. And then we're also interested in the sludge production rate, mainly to consider the reaction from the calcium carbonate or magnesium carbonate into the calcium sulfate or magnesium sulfate. Okay, so this is a general idea about the sulfur dioxide control. Okay, so from this class, we're going to learn about the nitrogen oxides, and we also call them as SOx. Okay, so you can see basically the SOx would mean a group of nitrogen oxides. So since we have already learned the nitrogen dioxide, I think there can be some similarities and distinctions from the nitrogen oxides. Okay, so the similarities with the nitrogen dioxide or nitrogen trioxide. So generally we call these as SOx. Okay, so the similarities with the SOx is actually both of them are regulated as a criteria air pollutant, right? It's going to damage the human health. And also it can damage the property by forming the acid rain. I mentioned that the acid rain involving the SOx are going to be sulfuric acid, right? And also the acid that's involving the nitrogen oxides are going to be nitric acid. And both of the acids are very strong acids, okay? So it can corrode a lot of things. And once it falls on the skin of the people or animals, it's going to damage the skin. So that's why they're regulated as the criteria air pollutants. So this is their similarity. And there are quite many distinctions, okay? So whatever we mention about SOx, it's just 2 species. One is a sulfur dioxide, one is a sulfur trioxide. And sulfur trioxide is basically oxidized from the sulfur dioxide when it gets in contact with the oxygen in the air. But when we're talking about the NOx, that is going to be a group of oxides. Okay, so here I'm listing the commonly seen nitrogen oxides, which can include nitrogen monoxide, nitrogen dioxide, N2O, N2O2, so on and so forth. So each of them may be stable under certain temperature. Okay, so for example, the nitrogen oxide, this is the most stable form of the nitrogen oxides when it's at high temperature. Okay, at high temperatures, nitrogen monoxide is the most stable form, and at low temperatures, nitrogen dioxide is the most stable form. Maybe in the intermediate temperatures, in certain temperature ranges, so each of them will have their optimal temperature window or pressure window, so that they're existing in the most stable form. Okay, and in terms of the sources, there are also some differences. So we mentioned that for the SOx, 1/3 of them are coming from the oil refinery. Okay, this is about SOx. And 2/3 of them are coming from the coal-fired power plant. Okay. But for the NOx, so half of them are actually coming from the vehicles. It can be just our car engine. So that's why we have to do the engine emission test, I think every year or every 2 years, right? So, and among the remaining half, 1/3 of them are coming from the stationary sources. So the stationary sources would mean industrial plants, including the coal-fired power plants. Okay. And some other industry. So these industry will generally involve high temperature process. Okay. So you can see that in terms of sources, the emission of the NOx is a little bit different. So we mentioned that for the SOx, or sulfur dioxide, sulfur trioxide, we mentioned that they're not coming from the vehicles because the oil refinery already deal with the problem, right? But for the NOx, it's going to be difficult to deal with them in this way. That's why more fraction of the resources are more fraction of the sources are coming out of the vehicle. So we mentioned about the importance of the NOx, but how are they being formed? Okay. So also similar to the sulfur dioxide or sulfur trioxide. So basically, for some organics, let's say the fossil fuel, there can be sulfur that's incorporated into the fossil fuel there. And similarly, there can be nitrogen that's incorporated into these fossil fuels. So once we combust them, so we can get nitrogen oxides. Okay, so these are the existing nitrogen in the fuel. So this is one way to form it. And there's another way, and also very important way in terms of forming the nitrogen oxides. So if you just look at the composition of the nitrogen oxides, it's composed of nitrogen and oxygen, right? And we also know that in our ambient air, it's mostly composed of nitrogen and oxygen, okay? Under normal condition, under ambient temperature, these two will not react with each other. Otherwise, it's going to be fireworks everywhere around us, okay? So under ambient condition, the two are not going to react with each other. But under high temperature, they two can react with each other. And then, so the most stable form, as we mentioned, they're going to form nitrogen monoxide. So that's why we call this part of the NOx formation as the thermal NOx. And this part of the nitrogen oxides, we call them as the fuel NOx. Okay, so the thermal NOx and fuel NOx are the two most important mechanisms to form nitrogen oxides. And basically, that is an important source of the nitrogen oxides in the ambient air. Okay. So let's just talk about them one by one. Okay. So during this process, I also try to refresh you with some important concepts regarding the reaction equilibriums, and also the kinetics. Okay, so here it basically gives you the equilibrium constant of the formation of NO and NO2. So here we're talking about the thermal NOx. So thermal NOx is going to be the reaction between nitrogen and oxygen. Okay. So here I'm giving you the equilibrium constant. So for those who haven't taken the 2601, the fundamentals of environmental engineering, so the equilibrium constant just means what is the concentration of the species under equilibrium condition. Equilibrium just means, let's say, if we are talking about several species reacting with each other. So the equilibrium condition just means we keep these species and maintain it for infinite long time. It can be years, tens of years, hundreds of years. So finally, they're going to reach to a final state. And we call that final state as the equilibrium condition. Okay, so that determines the final concentration. So the equilibrium constant determines the final concentration of all of the species. Okay. So for example, if we're talking about a reaction between A number of P reacting with B number of Q, forming C number of N and D number of R. So the equilibrium constant for this reaction is going to be defined as the concentration of N to the power of C, concentration of R to the power of D, divided by the concentration of P to the power of A and concentration of Q to the power of B. Okay, so the equilibrium constant is a defined value. It's not going to change as a function. Let's say it's going to change as a function of temperature, but other than that, it's not going to. It's a constant. Okay, so once we determine what is a constant here, then theoretically we should be able to calculate what is the concentration of all of the species, or at least what is their relationship in this reaction, in this equation here. Okay, so the same can be applied for the formation of the NOx. Okay, so we can basically separate the reaction or the formation of NOx species into two reactions. So the first reaction is the reaction between nitrogen and oxygen to form two number of nitrogen monoxide. Okay, and the second reaction is the oxidation of the nitrogen monoxide to form nitrogen dioxide, right? And for each of the reaction, they have a equilibrium constant, and the equilibrium constant is going to be a function of temperature. Okay, so theoretically, with this table here, we should be able to calculate what is the concentration of the NOx under certain temperature. So here we have an example problem. That's the example 6.1 in your textbook. So basically, so the problem wants us to just consider the reaction 14.6, which is the first step forming the nitrogen monoxide. Okay, and it wants us to calculate the equilibrium concentration of the nitrogen monoxide for a flue gas at 1500 Kelvin. Okay, under this temperature here, and at a pressure of 1 atmosphere, with a composition of air with 76% of nitrogen, 4% of oxygen, 8% of carbon dioxide, and 12% of the water vapor. Okay, so basically from the condition here, we can get the concentration of nitrogen and oxygen. Okay, and if we list out what is the equilibrium constant of this reaction here, you can find out that basically the Kp is going to be equal to nitrogen monoxide concentration to the power of 2 divided by the nitrogen concentration, and then divide by the oxygen concentration. Okay, and we can see that this equilibrium constant for this reaction here is 1.1 multiplied by 10 to the negative 5. Okay, so we further know that the concentration of the nitrogen is 0.76 and the concentration of oxygen is 0.04. Okay, So if we plug in these values here, so we can find out that the NO concentration is going to be basically square root of 1.1 multiplied by 10 to the negative 5 multiplied by 0.76, 0.04. So that is going to be 5.78 multiplied by 10 to the negative 4. Okay. And what this also means is going to be 578 ppm. Okay, so this is the equilibrium constant, or equilibrium concentration of the nitrogen monoxide. Okay, and similarly, let's say if you're interested in the concentration of the nitrogen dioxide, so how do we do that? How do we calculate this? So we can further refer to this equilibrium constant, right? So that is going to be 1.1 multiplied by 10 to the negative 2, say Kp, and that is going to be equal to the concentration of NO2 divided by the concentration of NO multiplied by the concentration of oxygen to the power of 0.5. If you look at this equation, the power here is 0.5, right? So we should use this term to represent the equilibrium constant. So now we have the concentration of the here. We have the concentration of the nitrogen monoxide. So we also have the concentration of the oxygen, 0.04, right? So if we plug in the value, we can find out that the nitrogen dioxide concentration is going to be 1.27 multiplied by 10 to the negative 6, which means it's 1.27 ppm. Okay, so this is I would say an evidence which shows that the nitrogen monoxide is going to be a more stable form compared to the nitrogen dioxide at high temperatures. Okay, so for example, from this problem, you can see that at least under 1500 Kelvin here, you can see there's a higher concentration of the nitrogen monoxide, while there's a lower concentration of the nitrogen dioxide, right? So then we may wonder, what's going to happen if it's under a lower temperature, okay? So let's say, for example, let's assume that this is what happened in the coal-fired boiler, right, in the high temperature boiler. Okay, so if we already have this flue gas that contain nitrogen, oxygen, and some nitrogen monoxide and fewer nitrogen dioxide, okay? So let's say if we reduce the temperature to 300 Kelvin, okay, originally it's 1500 Kelvin, and we reduce the temperature to 300 Kelvin, okay? So one thing we can directly notice is that the equilibrium constant for the second reaction here is much, much larger than the value here, right? So if we write out the form of the equilibrium constant, that's going to be the concentration of NO2 divided by the NO, and then oxygen concentration to the power of 0.5, okay? So with this significantly larger equilibrium constant of this second reaction, what that means is either the nitrogen dioxide concentration is going to increase, or the nitrogen monoxide concentration is going to decrease, okay? So this is an indicator showing that under low temperature, the nitrogen dioxide concentration or the nitrogen dioxide may be more stable, mainly because the rate constant or the equilibrium constant is much larger compared to the high temperature condition. So we can indeed test this out, okay? So let's assume that the nitrogen monoxide concentration doesn't change. Okay, so it's at 578 ppm. And then we suddenly change the temperature from 1500 Kelvin to 300 Kelvin, okay? So we can plug in this equilibrium constant and find out what is the nitrogen dioxide concentration under this temperature, okay? So similarly, we can write out this equilibrium constant at 300 Kelvin. That's 1.4 multiplied by 10 to the 6, Okay, so this is 300 Kelvin. Here we're talking about 1500 Kelvin. Okay, so that is going to be NO2 concentration divided by NO, and then multiplied by oxygen concentration to the power of 1.5. And then we need to plug in the nitrogen monoxide concentration in here. Okay, so you can find out that the nitrogen dioxide concentration is actually 161.84. Okay, and this number doesn't make sense at all, right? So here we were all talking about the fraction, the volume fraction, or the partial pressure or partial volume of all the species, right? So everything has to be lower than 1. For example, nitrogen is 76%, which means that it's 0.76, right? Oxygen is 0.04. So these are volume fractions here. So the number we get are also volume fraction. This volume fraction is much, much larger than 1, okay? So what this means is we're not going to generate this amount more of the nitrogen dioxide. So what this means is that under this condition, nitrogen monoxide concentration is going to be much lower than 578 ppm. Okay, so has to be lower than 578 ppm. Okay, and what this also means is that all of the nitrogen monoxide are going to get converted into nitrogen dioxide. So that's why under low temperature, the nitrogen dioxide is a much more stable form. Okay, so based on these equilibrium constants, we can basically prove that at each temperature, each type of the or each species of the nitrogen oxide are going to have their own stability, and at low temperatures, nitrogen dioxide is going to be the most stable form. Okay, so this is also the reason why if you check the NAQS or the EPA regulated concentration of the nitrogen oxides, you can find out that it actually just regulates the nitrogen dioxide. Okay, so they don't regulate nitrogen monoxide here, mainly because nitrogen monoxide is not stable under ambient condition. And we, when we evaluate the air quality, we just evaluate it under ambient temperatures, right? We don't evaluate it at 1500 Kelvin. We just worries about what is the typical concentration of these air pollutants. So one thing we can also find out is that from this calculation, if we assume that all of the nitrogen monoxide are being transformed into the nitrogen dioxide, then the nitrogen dioxide concentration in the flue gas are going to be somewhere around 578 ppm, right? So if we compare this number to the regulated number, so the value we got is 578 ppm. So you can find that this value is much, much larger than the regulated concentration of the nitrogen oxides or nitrogen dioxide, right? So this means that we have to build some NOx control systems to remove the nitrogen oxides from the flue gas. Okay, so we're going to talk about these control devices in our next class. So this is the equilibrium condition or equilibrium concentration of the nitrogen oxides or nitrogen dioxides. But one thing we also mentioned is that whenever we talk about equilibrium, so that's going to take a very long time, right? That's going to, as I was mentioning, that's going to take maybe days, months, or even years. So we're talking about this kind of time scale. But if we want to understand what is the concentration of the nitrogen monoxide or nitrogen dioxide from the car engine, or from the coal-fired power plant, those processes are very fast, right? We're not going to, let's say, if we want to burn a gallon of the gasoline, we're not going to burn it under a equilibrium condition and wait for a year to evaluate what is the concentration of the nitrogen monoxide. So those processes are very fast, right? So for these transient processes, we have to characterize them in a different way. So basically, we need to know what is the reaction rate, okay? So before we talk about the reaction rate, here we have another table showing how the equilibrium conditions affect the concentration of the nitrogen monoxide and nitrogen dioxide. So what this means is we take an air sample, let's say just the air outside, right? We take, let's say 1 liter or 1 cubic meter, so on, right? So we just put it in a container and then put it in a furnace. Inside the furnace, we can control whatever temperature we want, okay? And inside the furnace, we can also measure what is the concentration of the nitrogen monoxide and nitrogen dioxide under equilibrium condition. We can wait for a long time to characterize their concentrations. So you can see that under normal temperature or ambient temperature, if we just put a mixture of air, then the concentration of NO and NO2 are very low here, okay? So basically, it means that there's not going to be a lot of NOx inside the air, right? We're talking about these numbers in ppm. So even in ppm, the concentration of NOx is 2.1 multiplied by 10 to the negative 4, right? So that means it's basically 0.21 ppb, right? This is very low amount of the NOx. But still, you can see that under low temperature, the concentration of NO2 is much higher than NO, which means that NO2 is the more stable form under ambient temperature. But if we raise the temperature of this box containing the air, we raise it to around 1600 Celsius, 1873 Kelvin, you can see that the trend is reversed, right? The NO concentration is much higher than NO2. I mentioned that at high temperatures, the nitrogen monoxide is a more stable form. And also the concentration of these species become higher, right? So the concentration of the nitrogen monoxide is 6100 ppm. This is very high fraction of the nitrogen monoxide in the air. So you can see why we call this as the thermal NOx. So thermal NOx means if we raise the temperature, even if they're just air, which are stable under ambient conditions, they're going to form nitrogen oxides at high temperatures, okay? So this is for air. So we can also take a sample of the flue gas out of a coal-fired power plant and then do the same, right? So you can see under low temperature, still the nitrogen monoxide concentration is lower, right? So it has this type of relationship, right? NO concentration is much higher than the nitrogen dioxide concentration, much higher than nitrogen monoxide concentration, right? And if we raise the temperature to high enough, then we have this reverse trend of the concentration here. Okay. So again, this is talking about the equilibrium condition. And we can only do these equilibrium tests when we put it into a furnace and then let it stand still for infinitely long time, right? So we mentioned that the diesel engine or car engines or the coal-fired power plants, they will never reach to equilibrium, mainly because this is just a really fast reaction, really fast process in the combustion process, okay? So that's why we have to calculate what is the formation rate of these nitrogen monoxide or nitrogen dioxide species. So to calculate their rate, we have to analyze or separate the reactions into these element reactions, okay? So instead of letting the nitrogen to react directly with oxygen, so actually this reaction is separated into several steps here. So first, the oxygen get activated to form oxygen radicals, and similarly, nitrogen can also get activated to form nitrogen radicals. And these radicals can react with these molecules to form the nitrogen monoxide. So these right? You can have the forward reaction, you can also have the backward reaction. And there can also be the participation of the hydroxyl radicals, okay, or OH radicals. So these can also be forward and backward reactions. So to calculate the reaction rate, I can also write out some notes here. So if you haven't taken the 2601, so let's say if we write out this equation again, basically P plus Q going to N plus R, then the reaction rate, or the rate of formation of the N, let's put it this way, A, B, C, D, okay. So the reaction rate of N is going to be equal to A, it's going to be equal to the concentration of P to the power of A, and then concentration of Q to the power of B, and then there's going to be a rate constant, okay. And if we're talking about reversible reactions, let's say if it's K plus, this is K minus, and that's going to be further equal to K minus concentration of N to the power of C multiplied by concentration of R to the power of D, okay. So this is the reaction rate of the species N here. And to calculate how much of the species N are being formed over a certain period of time, then we can just multiply this Rn multiplied by time, okay? So the concentration of N is going to be equal to this term, which is the rate of the, basically the formation rate of the N multiplied by time, right? Because rate always have the unit of mole per meter cube per second. Okay, so if we multiply this term by time, then we can calculate how much, what is the concentration of the N after a certain period of time. Okay, so for the formation of the nitrogen monoxide, so we're talking about this reaction here. Okay, so for this reaction here, if you read through the textbook, page 530, so we can also make some assumptions regarding the formation rate of the nitrogen radicals. So we made an assumption called the quasi-steady state assumption. Okay, so if this assumption works, right, for this type of reaction, then the formation rate of nitrogen monoxide is going to be twice of the rate constant for this forward reaction of the first reaction, multiplied by the concentration of nitrogen molecules or nitrogen species multiplied by the concentration of the oxygen radicals, okay? So you can read through the textbook about how they derive this equation here. Because theoretically, if you consider the rate of reaction of nitrogen monoxide, then you have to consider the forward reaction of these species, the backward reaction of these species, and also the forward reaction of the second reaction, right? Backward reaction of the second reaction, and the forward reaction of the third, and backward reaction of the third. So it's going to be quite complex, but if we can assume that the quasi-steady state assumption works, which indeed it should work, mainly because the nitrogen radical is very unstable. So the assumption means that the formation rate of the nitrogen radical is equal to the consumption rate of the nitrogen radical, mainly because this is very active. So as soon as they're being formed, they're being consumed, okay? So if this assumption applies for this set of reaction, then what it means is that the formation rate of the nitrogen monoxide can be calculated by this equation. So this greatly simplifies the calculation of the reaction rates and determining this kinetic process, okay? So here we have an example again. So it's given a hydrogen flame at this certain temperature, where the mole fractions of nitrogen gas and oxygen atoms are 0.75 and 9.5 multiplied by 10 to the negative 4, right? And then one starts to calculate what is the initial rate of the nitrogen monoxide formation in this unit here, okay? So directly, we can just use this equation to calculate the formation rate, right? So this is a formation rate. We just need to find out what is the K plus 1. So it's already tabulated here. We just need to plug in the temperature in Kelvin, right? So this is a rate constant. We can solve that. And then we just need to find out what is the concentration of the nitrogen and what is the concentration of the oxygen atoms, right? But what we cannot do is we cannot directly put in these values here, because if you check the unit of the rate constant, it's using meter cube per mole per second, right? So let's say if we write out this unit here, then we know that the rate constant or the reaction rate has the unit of meter, have the unit of mole per meter cube per second. Okay, so what this means is that we need to plug in the concentration in mole per meter cube. Okay, so only in this way we can make the unit conserve on both sides, right? So that's why we cannot directly put in this mole fractions or the partial pressure or partial volume into this reaction. We have to convert this mole fraction into the moles per meter cube. Okay, so let me just outline this process here. So if we want to solve for A, then the reaction rate of NO is just equal to 2 times of K plus 1, the concentration of nitrogen multiplied by the concentration of oxygen atoms. So we know that K plus 1, let me just minimize this a little bit, 1.8 multiplied by 10 to the power of 8 exponential minus 38370 divided by T. Okay, and then we need to multiply that by the concentration of the nitrogen molecules and the oxygen radicals. So here we show that we have to plug in the absolute concentration, right? So now we have to go back to the unit conversion that we learned at the beginning of this class. So the moles per meter cube, if we represent that in parameter, that means NA divided by V, right? And what this problem gave us, the partial volume or partial pressure, that's NA divided by N. So basically we need to convert the NA divided by N into NA divided by V. So how do we do that? So the way we do that is using the ideal gas law, right? NA divided by N is going to be equal to, first we know the PV equal to nRT, right? So that's why N is going to be equal to PV divided by RT, okay? So if we plug that in, that's going to be NA divided by V multiplied by RT divided by P, okay? So if we plug this in here. So here we can get a direct conversion from the mole fraction into the mole concentrations or the absolute concentration, okay? And for this reaction, for this problem here, this is going to be a constant, right? So because the temperature didn't change, right? The pressure didn't change. We just need to plug in what is the ideal, gas constant. We know that that is 8.314, okay? So we can find out that this conversion is going to be equal to NA divided by N multiplied by 8.314 multiplied by 273.15 plus 1870 divided by 1.01 multiplied by 10 to the 5th. Okay, so here are just plugging in the values of the ideal gas law, I mean the gas constant, the temperature in Kelvin, the absolute pressure in Pascal, right? You can find out that this is NA divided by V multiplied by 0.176, okay? So this is how we can convert the mole fraction into the absolute concentration. And now we can start to plug in values. Okay, so we know that the mole fraction of the nitrogen gas is equal to 0.75. Okay, so then we can find out that the absolute concentration of the nitrogen, that is going to be 0.75 divided by 0.176. Okay, so that's basically the absolute concentration here. Okay, and similarly for oxygen radicals, that's going to be 9.5 multiplied by 10 to the negative 4 divided by 0.176. Okay, so with all of these information plug in, temperature 273.15 plus 1870. Okay, so with all of these information plugged in, you can find out that the R here, or the reaction rate, is 0.139 mole per meter cube per second. Okay, so this is the reaction rate of this process under high temperature. So we already solved for the reaction rate, and the second question asks us if this rate holds for a constant time of 0.03 seconds. And this indeed makes sense, right? So for car engines, we have certain number of rotations of the piston there, right? So it is operated at a very high frequency. So the time, actually the residence time is very short. And same thing applies for the coal-fired power plant. Okay, so the gas is not going to stay for infinitely long time under high temperature. So that's why we have to consider we cannot use the equilibrium rate constants, right? We cannot use the equilibrium constant to solve for the concentration. We have to use the kinetics to solve for the concentration of the nitrogen monoxide or nitrogen dioxide. So since we already have the rate, and if we know the time, then we can calculate what is the concentration of the nitrogen monoxide, right? So the way we do that is just NO is equal to rate of NO multiplied by time, 0.03, right? And then you have 4.17 multiplied by 10 to the negative 3 mole per meter cube. And this question asks us for what is the concentration in ppm, okay? So we need to further convert this absolute concentration into ppm, or the partial pressure, or the molar fraction. Okay, so the way we do that, is just multiply this number by 0.176. Okay, so you see the molar fraction is equal to the absolute concentration multiplied by the 0.16, and we have the absolute concentration here. So then we have 7.33 multiplied by 10 to the negative 4, and that means it's 733 ppm. Okay, so this is going to be a more accurate way to determine the formation rate or the concentration of the nitrogen monoxide, right? So here you can clearly see the difference between the reaction kinetics and also the equilibrium constants, right? So again, I want to point out that the equilibrium constant, we can only use that when we assume that it's under equilibrium. That's going to take a very long time to reach to equilibrium. And to more accurately determine the concentration of the nitrogen monoxide or nitrogen dioxide, we have to use the rate constants or the reaction rates to solve for what is the concentration of these nitrogen oxides. Okay, so this is the basically how the kinetics affects the formation of the nitrogen monoxide. And also from here, you can find out that we haven't discussed one thing, which is the time. So we assume that the time is 0.03 seconds for this problem, right? But you can see that if time increased by 10 times, okay, then what that means is that the concentration will also increase by 10 times. So that's why for these combustion engines, we want it to be operating in a very fast manner, right? We don't want to, if it's very slow, then we're going to accumulate more nitrogen oxides from this reaction. And actually, people put more thoughts onto the formation of the NOx from different, let's say, car engines or from the coal-fired power plants. So what they find out is that the nitrogen monoxide concentration is related to only a few parameters. Okay, so you can see that for this plot, they showed the concentration of the nitrogen monoxide as a function of temperature. So basically, this temperature is the flame temperature. Okay, and this is shown in Fahrenheit. Okay, so you can see that if, let's say, we just follow this line here. So what this line means is we let the gas mixture to stay for 0.1 seconds under this high temperature zone, under the high temperature zone of the flame. Okay, so what you can find out is that if the temperature increases, then the nitrogen monoxide concentration will also increase, and actually it increased very rapidly. This is shown in log scale, right? You see that from 3200 Fahrenheit to 3600 Fahrenheit, the concentration of the NOx increased by 100 times. Okay, so you can see that the nitrogen monoxide concentration is very sensitive to temperature. Right, the higher the temperature, the more the NOx or the nitrogen monoxide. But also, you can make an intercept in this way. Let's draw a vertical line. Okay, so this vertical line means let's just fix the temperature at certain number here. Let's say 3600 Fahrenheit. Then you can see that the residence time of the flue gas or residence time of the gas mixture will also significantly affect the formation of NOx, right? From 0.01 second to 1 second, the concentration also increased, let's say, around 60 times. Okay, so you can see that how the temperature and the time will affect the formation of the nitrogen monoxide. So these are the two parameters that determines the formation of NOx. And there's one more parameter, which is shown in here. So one more parameter, the other parameter is the concentration of the oxygen, okay? So here, what is showing is basically the NO concentration, again, the nitrogen monoxide concentration, as a function of the equivalence ratio. So you can think of the equivalence ratio as the oxygen that's required by stoichiometry divided by the oxygen in actual situation. Okay, so what this means is that, let's say we're trying to combust carbon here. Okay, we know that the carbon and oxygen are going to react with 1-to-1 ratio. Okay, so what this basically means is that the oxygen amount required by stoichiometry is going to be 1. But let's say if we provide twice of the air here, then the actual air concentration is going to be 2. Okay, so what this means is that the equivalence ratio is going to be 0.5. So that's why it shows air rich when the equivalence ratio is below 1. Well, if the equivalence ratio is larger than 1, that's fuel rich. Okay, so what you can find out is that, again, based on the time, you see if we increase the time, the nitrogen monoxide concentration increases. But also what you can find out is that the nitrogen monoxide concentration always peaks when the equivalence ratio is below 1. Okay, so what this means is that if we provide more air into the combustion, we may get more nitrogen monoxide coming out of the combustion. Okay, and this is also shown in the coal-fired power plant. So this is also showing the fuel equivalence ratio. Okay, so again, if it's equal to 1, then that means it's providing the air according to the equivalence ratio. If it's below 1, that means air rich. If it's larger than 1, that is fuel rich. And you can see that when there's air rich, we have more or higher percentage of the nitrogen converting into the nitrogen oxides. Okay, so if there's more air, then you're going to get more nitrogen oxides. So that's why the oxygen concentration will also determine the formation of NOx. Okay, so we can talk about this more in our next class. So that's all for this class, and let me know if you have any questions.